Hello, welcome again. We are solving GATE 2021 Aerospace Engineering paper. Question number 44 is hot gases are generated at a temperature of 2100 Kelvin and pressure of 14 MPa in a rocket chamber. The hot gases are expanded ideally to the ambient pressure of 0.1 MPa in a convergent divergent nozzle having a throat area of 0.1 meter square. The molecular mass of the gas is 22 kilograms per mole. The ratio of specific heat gamma of the gas is 1.32. The value of universal gas constant Ra is 8314 joule per Kelvin per mole per kilowatt per Kelvin. Okay. And the acceleration due to gravity g is 9.8 meter per second scale. The specific impulse of the rocket is dash second, round up to 2 decimal places. So here it is given as universal gas constant is given as 8314. So we know that Rm is equal to Cpm minus Cv, Cp minus Cv. Okay, Rm is molar, Cpm is Cp molar, and Cvm is Cm molar. Okay, so dividing both sides by Cp, so we'll get Rm by Cpm plus is equal to 1 minus Cv by Cvm, and Cv by Cp is your gamma. So Cp by Cv is gamma, that is 1.32. Okay, so 8314 divided by Cp is your so this will be 0.2424. Okay, so Cpm will be your 8314 divided by 0.2424. Okay, and Cpm will be your 34298 joule per kilomole already can. Okay, so that is the molar specific heat at constant pressure. Okay, and the specific heat at constant pressure is molar by molecular weight. So that is molecular weight is given as 22. Okay, so it will be so the Cp will be your 1559.03 joule per kilogram per degree Kelvin. Okay, so that is the first thing that we have to calculate, that is Cp of the gas. Okay, now the ambient pressure is 0.1 MPa and the hot gas is generated at 14 MPa. So the pressure ratio is 14 by 0.1 and initial temperature is 2100 Kelvin. So we can find out the exit temperature by using isentropic relation. So P naught by PA, T naught by TA. So 14 by 0.1, so it will be 0.32 by 1.32, or T naught is 2100, TA is, we can find out. So T comes out at 633.79. Okay, so that is your T naught is your segregation temperature, TA is your ambient temperature. Okay, so the exit temperature, P is your exit temperature. Okay, so exit as the exit velocity can be found out by change in enthalpy from stagnation relation to exit condition. So that is so exit velocity will be 2 Cp T naught minus Ta. Cp minus T naught minus Ta is your change in enthalpy. If you multiply by 2, that will be equal to V square. So Cp T naught minus Ta will be equal to V square by 2, and if we multiply by 2 and root it, so then we can have exit velocity. So the exit velocity is 2318 meter per second, and specific impulse is defined as thrust by weight. So this is mv by mg, so v by g, so that is 2138 by 9.8, that is 218.17 seconds. Next, question number 45. A twin spool turbofan engine is operated at sea level. PA is 1 bar and TA is 288 Kelvin. The engine has separate cold and hot nozzles. During static thrust test at sea level, the overall mass flow rate of air through the engine and the cold exhaust temperature are measured to be 100 kg per second and 288 Kelvin respectively. The parameter for engine are fan pressure ratio 1.6, overall pressure ratio 20, bypass ratio 3, turbine entry temperature 1800 Kelvin. The specific heat at constant pressure Cp is 1.005 kilojoule per kilogram per degree Kelvin. The ratio of specific heat gamma is 1.44 here. Assuming ideal fan and ideal expansion in the nozzle, the sea level static thrust from the cold nozzle is dash kilonewton, round of to 2 decimal degree. So here the temperature ratio is here the sea level pressure is 1 and 1 bar and temperature okay. As the pressure ratio, overall pressure ratio is 20. Okay, so and the fan pressure ratio is 1.6. So the across the cold nozzle or the fan, the pressure ratio is 1.6. 1.6. Okay, so this is not 5, this is only 1.6. Okay, so 1.6 0.4 by 1.4, or now that ambient temperature is 2. First of all, the air is entering in the fan, so that is the stagnation temperature 288, because it is at the sea level, so it is not flying, so it means the this is stagnation temperature. So T02 or temperature at the exit of the fan is 329.29 Kelvin, and velocity at the exit is here Cp 2 Cp T0 minus T02 minus T01, or so this is the velocity 288.39 meter per second. Okay, and the bypass ratio is given as 3. So the mass through the cold total mass is given as 100 kg per second. So mass through the cold nozzle is m into b by b plus 1. So that is 75 kg per second. So that is mass is flowing through the cold nozzle, that is not flowing through the cold nozzle. So the static cold thrust is 75 into that that velocity, because inlet velocity is 0, so exit velocity is this, so static cold thrust is 75 into that changing velocity itself. Okay, so that is 21632 Newton or 21.632 Newton. So we have to only calculate the cold thrust. Okay, so that is the answer, 21.632 kilometers.